Good evening, sir. We are Group 39, and today we are presenting you the paper Adaptive Fusion of Multi-View for Graph Contrasted with Recommendation. So, our group members are me, myself, Dhruv Agarwal, Joel Joseph, and Vijender Singh Bhati. So, from here, Joel will tell you the introduction of our project.
So this is the introduction of our project, which is based on recommendation systems. So recommender systems are essential in mitigating information overload by offering personalized suggestions. Collaborative filtering assumes users with similar behaviors to be having similar preferences. In this, matrix factorization was an earlier collaborative filtering model which was used using embeddings and deep learning extended this approach with neural networks to improve embedding quality. In this graph, neural networks further enhanced user item representation by capturing higher order connectivity. More recently, graph contrastive learning combines GNNs with contrastive learning to improve recommendation performance through augmented user item representations. And the key challenges we are facing in this existing graph contrasting learning methods often introduce noise through random perturbations. Lack of user preference modeling during the representation learning process. Next slide. So, in order to mitigate these drawbacks, we propose AMCGR, which is Adaptive Multi-View Graph Contrastive Recommendation, which necessarily uses 4 view generators for edge view learning, which is weight adjustment, feature transformation, neighbor aggregation, and attention mechanism. This implements an adaptive multi-view fusion module to combine informative views, defines preferences during learning for better user item representation. As an impact, this AMCGR achieves 10% 10% plus in recall and NDGC across multiple datasets. Next slide. This is the related work which is done in this field. The first one is the graph neural networks in collaborative filtering, which has demonstrated strong performance in learning representations by capturing higher order connectivity in user item graphs. Models in this include like GCMC, which uses graph autoencoders for matrix completion, while NGCF enhances interaction modeling by incorporating collaborative signals. One more model, which is STGCN, improves pole start performance with a stacked GCN architecture. To address this scalability and over smoothing approaches like GCCF, Light GCN, and HGCF have optimized GCN architectures. In this, Light GCN simplifies GNNs by removing nonlinear activations, becoming a popular CF method. SIMREC further adapts GNN knowledge transfer for smaller networks. Despite all these advances, data sparsity remains a challenge in GNN-based recommendations. Next slide. Another related work in this field include contrastive learning in recommendation. This has especially become popular for tackling data noise and label sparsity in recommendation with detailed applications in sequential, multi-interest, and multi-behavior recommendations. In CF, CL is often combined with GNNs to generate user item recommendations. In collaborative filtering, one more method like SGL uses data augmentation, but this especially has a risk of losing important information and worsening sparsity issues for inactive users. So more recent approaches like SCCF and NCL employ strategies like to strategies to construct contrasting views, while SimGCL and XSimGCL add noise to embeddings, which drastically improves CL without complex augmentations. However, these methods still produce noise, limiting their adaptability in various recommendation scenarios. Slide. Okay, so these are the preliminaries for the experiment that we are about to conduct, in which users are represented as a set of items. Users as U1, U2 to UM.
of a like particular user over other users. So this is for about the first layer. In the second layer is adaptive multi-view fusion layer. Here we have different types of edge weights we obtained from the first layer. So the different type of edge weights are, first is a view shared edge weight. This edge weight reflect relationships consistent across all views. And we first extract the view shared edge weight through the attention mechanisms, where the attention weight of different kinds of views are this. So we can see the formula here, where the W1 belongs to R and B1 belongs to R. They are learnable parameters that we learn from our model. Second is the view specific edge weights. These reflect unique user item relationships based on the user intent. They are calculated by the formula Wk equals to Wk minus Ws, where the W upperscript K are the view specific edge weight for view K. And the third edge weight we have is the fusion of the edge weight of the first two edge weight we have learned. It is the fusion of the view specific edge weight and the view shared edge weight. The third layer we will talking about is the preference refinement layer. The preference refinement layer objective is to create a preference matrix P. In the preference matrix P, we give more weight to the items specific to one user than the items that are not specific to the user. These are the formula to calculate the matrix. The fourth layer we have is the contrastive learning layer. It helps us to improvise the AMGCR model by contrasting the learned embedding of user and atom from the original and contrasted views. So we define the loss function in this layer. The loss function is as follows: minus log exponential of this term divided by exponential of this term, where the ZU is the original embedding layer and GU is the embedding we get from the contrastive learning layer. And phi is the similarity function, tau is the temperature parameter, and GUI is the contrastive view embedding for user UI. Similarly, we can get LVCL, and if we combine LUCL from this formula and LVCL, we will get the LCL, that is the combined loss in the contrastive layer. So here Vijay will tell about the inference and optimization.
Yeah, so now coming on to the inference and further optimizations. During inference, our model predicts the interaction probability Yij between user UI and item Vj by calculating the dot product of the embeddings given by Yij equals Z mu I dot ZVJ. Optimization involves a multitask objective that combines three main goals, which are BPR recommendation, contrastive learning, and preference refinement. And the total objective loss is given by the expression L equals L PPR plus lambda 1 LCL plus lambda 2 LPR plus lambda 3 modulus of theta squared. The BPR loss function used for ranking is defined as L BPR equals minus of summation log delta yi minus j minus yin, where yi, j, and yin are scores of positive and negative items respectively, and delta is represents the sigmoid function. This multi-objective optimization framework enables the model to learn user item interactions more effectively, thereby enhancing recommendation and refining user preferences. Next slide. Yeah, so coming on to the time complexity analysis, our model begins with agency matrix normalization, which has a time complexity of order of E, where E is the number of edges. Additionally, the light CGL requires SVD, which is singular value decomposition, to create a contrastive view, and adding an additional overhead of order of O of Q into E complexity. Then the batch training complexity includes augmentation complexity, where we generate four edges weights based on the interaction graph, adaptively fuse them, and refine the view, leading to a complexity of order of 4 ED, which includes SGL, which requires two augmentation having the complexity of order 2 rho E, while DCCF distills intent factor across layers, which have an additional time complexity of order of 2 E LD. NCL uses clustering for prototypes which in itself has an order of O of M plus N times D, while SIM-GCL and XSIM-GCL add the noise to embeddings, which in turn has an time complexity of order of M plus N times D. And the GNN application part, our approach applies this GNN to both the original and contrastive views with 4 ELD complexity comparatively. SGL and SIM-GCL utilizes a 3 GNN setup resulting in order of 6 ELD complexity. Next. So all the methods utilizes BPR loss, where each batch includes B interactions and random negative samples, giving the same time cost across models. Contrastive loss model complexity. Our model contrast positive and negative samples per batch with order of BD plus BTD complexity. DCCF contrasts all the nodes across layer per batch, which have order of B M plus N LD, and NCL, which employs K-square prototype contrastive learning, adding an overhead of BK square D complexity. While XSIM GCL is lightweight and effective, AMGCR stands out in terms of time efficiency and competitiveness across these methods. Next. Here we review AMGCR's evaluation using real-world data. We use the Amazon Books dataset, capturing user book interactions on Amazon. Following DCCF's pre-processing, user item interactions are extracted and split into training, validation, and testing sets, with a ratio of 70-20 is to 10. Coming on to implementation metrics, our experimental setup involves implementing in PyTorch, optimized with Adam Optimizer, which had a learning rate of 0.001. The hyperparameter settings were as follows. Embedding size was D equals 2, batch size was 4096, and temperature was 0.2. GNN layers L were selected from 1 to 3. AMGCR specific parameters were following: lambda in 0.1, 0.5, lambda 2 in range 0 to 1, and lambda 3 in range 10 power minus 7 to 10 power minus 5. Evaluation metrics and protocols. Metrics: recall K and NDGC K with K equals 20 to 40. Protocol: all rank protocol ranking test items against all unobserved items. Hardware specifications were as follows: experiment run on Linux with a 32-core CPU, 24 GB NVIDIA 4090 GPU, and 125 gigs of memory.
So now we will do a compressive performance analysis of the AMGCR model. This performance analysis evaluates the AMGCR model based on two key matrices. First, we will compare the accuracy. Second, we will compare the time taken of the AMGCR model. So first is that we do training process for 20 epochs because of the GPU limitations, and the loss over different epochs will calculated. So as we can see, for epoch 0 the loss is 4.85, epoch 1 it is 3.86, and at last for epoch 20 we have lost 3.58. So we will do two evaluation matrices. First is recall and second is NDCG matrix. So for the validation matrices, we have recall for the first 20 suggestions. It is basically improved from 0.0607 to 0.09. and the NDGC has improved from 0.0357 to 0.0581. And similarly, we can see for the top 40 recommendations, we have the recall and NDGC as 0.1468 and 0.0726. This result demonstrated a significant increase in both recall and NDGC matrices as we move from epoch 1 to epoch 20. The final testing matrix result are for 20 we have 0.09% accuracy. For NDGC at the rate 20, that is 20 recommendations, we have 0.05. For recall for top 40 recommendations, we have 0.14. For NDGC's top 40 recommendation, we have 0.0921% accuracy. So if we do the comparative analysis, the AMGCR model demonstrate notable improvements against baseline methods, particularly GCL-based methods, highlighting the model of robustness in leveraging learned argumentation and user preference refinements. This indicates that AMGCR model is capable of capturing richer semantic information and adapting dynamically to user preferences. The time taken in our process is approximately 5 minutes 30 seconds per epoch. So the total time taken is 109 minutes for 20 epochs. The training time is reasonable considering the model complexity and the dataset size. The efficiency is like time taken per epoch is like considerably stable around 20 epochs. So now we will do a hyperparameter analysis. We have basically two parameters, latent dimensionality and second is the batch size. So performing for 32D and 64D on epochs over 5, we have these results. For epoch 0, we have loss of 4.85. The validation recalls are 0.06, 0.09 for recall 20 and recall 40 respectively. For NDCG, we have 0.03 for NDCG 20 and 0.04 for NDCG 40. And similarly for epoch 1, we have 3.86 loss. And from epoch 2 to 4, our model continued to converge with reduction in loss values and improvement in recall and NDGC values. So the final testing results for D32 are 0.08 and 0.13 for recall 20 and recall 40. And for NDCG, we have 0.06 and 0.08 for 20 and 40 respectively. And similarly, for 64 dimensionality, we have these results. For epoch 0, we have loss of 4.58. As we can see earlier, for epoch 0, we have loss of 4.85. Now we have loss for 4.58. So the loss is decreased. And similarly, the SVC validation recall and validation NDCG is increased as compared to previous case. So it means the model is improving as we increase on D. The final testing results are 0.1045 and 0.1556 as for recall 20 and 40 and 0.08 and 0.09 for NDCG 20 and 40 respectively. As we can see in the graph also, these are the for D equal to 32 is this blue line, and d equal to 64 is this orange line. As we move over epoch 0 to 4, the loss is decreasing gradually. And this is the breakdown of loss components. We have actually two types of losses: loss BPR and loss CL, and loss PR. So this is a graph for the different breakdown loss components over epochs, and the validation recalls over epoch is also like increasing and it's remain constant, which tell us the model is performing good on our data. And these are the validation anti-CG values over different epochs. These are the final test recall comparisons. As we can see, like D64 having has more recall as compared to D32 top 20, and similarly D64 top 40 has more recall as compared to the D32 top 20. And similarly, we can see the same type of result in the NDCG comparisons. That is for D equal to 64, the recall 20 value score is more than D20 recall 20 value. And similarly for the recall 40, D64 value is higher as compared to the D32 value. And second hyperparameter we need to tune is batch size. The batch size refers to the number of training samples processed before the model internal parameters are updated. Selecting the appropriate batch size is vital for ensuring efficient training and convergence of the model. The smaller the batch size often result in more frequent updates to the model parameters, which can lead to noisier estimate of the gradient. These laws can sometimes help escape local minima, but can also lead to unstable training. Conversely, a large batch size, example 4096, allow the model to compute a more accurate estimate of the gradient, leading to smoother convergence. However, it also requires more memory and can slow down the training process, since fewer updates are made per epoch. So we have done four batch size tuning for 1024, for 2048, for 4096, and 10240. In the first batch size 1024, the model parameters final testing results are for test recalls. We have 0.079 and 0.0612. For NDCG, we have 0.0276 and 0.353 scores for the 20 and 40 respectively. For 2048, we have the final testing results as 0.0489 and 0.07 for recall, 20 and 40 respectively, and 0.03 and 0.04 for NDCG score, 20 and 40 respectively. For batch size 4096, these are the result over epoch 0 to epoch 5. The final testing results are 0.09 and 0.13 for recall 20 and recall 40 respectively, and NDCG 0.06 and 0.08 for recall 20 and 40 respectively. Similarly, for 10240, we have this testing results as for recall 0.07, 0.11 for recall 20 and recall 40 respectively, and NDCG score as 0.05 and 0.07 for 20 and 40 respectively. As we can see, the performance for this batch size illustrated the decline compared to the 4096 batch size, indicating potential overfitting or lack of sufficient granularity and updates. As we can see in the graphs, we have the highest score for the 4096 case. We have the highest recall score, and lowest for the 1024 and 2048 batch size. And similarly, the similar case we can see in NDCG comparison. So our optimal batch size is come out to be 4096. And similarly, for in the test case, the recall comparison for different batch sizes are as follows. Here also we obtained for the 409 batch size, we have a higher recall and NDCG score as compared to the other batch sizes. So Joel will conclude with the conclusion.
So as a result of this project, we present a novel recommendation model which is based on graph contrastive learning, termed AMCGR, Adaptive Model Graph Contrastive Learning. This model leverages adaptive augmentation techniques to enhance its learning capabilities for recommendation tasks. We especially have developed 4 view generators that effectively learn its ways for constructing contrastive views, addressing the common challenge of noise introduction seen in existing methods. And we also introduce an adaptive multi-view fusion module and a preference refinement strategy that integrates the 4 types of edge weights. As a result of this integration, the model is empowered to better capture the preference information between users and items throughout the learning process, ultimately improving its representation capabilities. Our experimental results on the Amazon book dataset, which it demonstrates superiority of our model compared to existing approaches. So on moving forward, we aim to further optimize the model by reducing its time complexity and increasing its efficiency. Additionally, we plan to explore the refinement of learnable perspectives to advanced digital-based methods, aiming for even better performance in recommendation systems. So with this, we conclude this project. Thank you.
Thank you.
Thank you, sir.
बस एक और फेस है क्या इसका
क्या
प्रोजेक्ट का एक